The statement reads, a long cylindrical shell of radius r carries a uniform surface charge plus sigma naught on the upper half and an opposite charge minus sigma naught on the lower half. Find the electric potential inside and outside the cylinder. We know that the potential should have the form of this from solving Laplace's equation in cylindrical coordinates. As always, there goes our favorite boundary condition. So to find the electric potential both inside and outside the cylindrical shell, what we need to do is find the coefficients. To start, let's consider some of the physical constraints of the system. Inside, where S is less than R, this is a region where the natural log and S to the negative k, or 1 over S to the k, blow up at the origin. And this isn't allowable for a physical system. So automatically we know that the coefficients B sub naught, C sub k, and D sub k must be 0 in order to account for this. Now if we look to the outside where S is greater than R, again we see that Ln and S to the positive k blow up as S goes to infinity. Again, this is not acceptable for a physical system. Thus we know that B naught and A sub k and B sub k must be 0 to account for this. Additionally, since V must go to 0 as S goes to infinity, we know that A sub naught is equal to 0. That just leaves us on the inside with A sub k and B sub k, and on the outside with C sub k and D sub k. So to solve for these, we know that we can use the continuity at S equals R and the boundary condition as given in the note, on the no slide. So continuity at S equals R means that these two summations need to be equated to each other. When we do that, we see that the coefficients on cosine are AK and CK, and the coefficients on sine are BK and DK, which allows us to express CK as a product of R with AK and DK as a product of BK with R. Next, what we can do is take the normal derivatives and use the condition at the boundary. Once we find these derivatives, then we can set that equal to the charge distribution. So V out at R and V in at R are as such, and we have to set them equal to negative sigma over epsilon. Subbing in the coefficient relations that we just found on the previous page, we can add them together and simplify. Alright, so after we subbed in CK and DK as a product of AK and BK, now we can factor out the R's and the K's and get them next to the summation. Once we boil it all down from algebraic manipulations and factoring, we get to the point where we have a piecewise definition of the charge distribution, which was given in the original problem and can also be seen in the diagram. This still leaves us with the coefficients AK and BK left to be solved. We can solve for this using a trick we've used in several other problems by exploiting the orthogonality of sine and cosine, or as what they call in the text, invoking Fourier's trick. For this first one, what we're going to do is multiply both sides by cosine, and we'll see what that turns out to be. Sine and cosine are orthogonal, so that goes to 0 on this domain, and cosine yield 0 or pi when k equals L or doesn't equal L. Then for k equal L, the charge distribution on the right-hand side needs to be evaluated piecewise for the plus or minus, and we see that the cosines simply cancel to 0. This leaves us with AL equal to 0. That's convenient. So now we have to exploit the orthogonality once again, but this time with sine. So we multiply sine of L to both sides and we evaluate. Similarly to cosine, sine and sine lead to pi when k equals L, and sine and cosine equal 0 because they're orthogonal. Then for k equal L, we evaluate the same way, but this time with the piecewise distribution, we see that the integrals are actually evaluated to 2 minus 2 cosine L times pi. And if you factor out a 2, you'll notice that it's 1 minus cosine, and cosine of any factor of pi is plus or minus 1. So we get a cancellation to 0 if L is even, or we get 4 sigma over L epsilon naught if L is odd. We will see this again when we recombine these coefficients into the summation, and that'll be important to note on the index. So putting that result together with the result of the orthogonality with the sine and cosine, we can say that BL is equal to this piecewise definition if L is even or if L is odd. So now we need to put it all together. Since we're looking at the case of L equal K, we can say that if AL is equal to 0, then so is AK. Thus, CK equals 0 from the relation we found earlier. Similarly, we know that BK is equal to this in its piecewise definition, and therefore we can find DK from the relation earlier as well. Just requires a little simplification. Now, if we're putting it all together in the summation notation, we have to do this piecewise for inside the cylindrical shell and outside. As we just found out, AK and CK both cancel to 0. Although this is piecewise defined, it'll help us simplify this down if we factor out things that are common, such as the sigma is you're indexing over the same for both cases. So we factored out the summation symbol, but note that in order to apply BK and DK, we had to change the index to odd values only. Otherwise, there's 0 elsewise. Okay, so once we plug BK and DK in and simplify it down, we see that we can factor out again 2 sigma r over pi epsilon naught. The index k squared must stay within the summation bounds, and then we're left with sk, or 1 over sk, with an rk, or 1 over rk, which just gets combined as you see here. So as you see, this cleans up fairly nicely for the big mess it was finding those coefficients.